Now we're going to look at continuously compounded interest, which is a type of interest that is different than your typical interest. Continuously compounded interest is when the interest is added continuously every instant throughout the year, and so then you're making interest on top of your interest on top of your interest, and it just compounds quickly, and you end up with more money in the end. So look at in the green here, it says continuously compounded interest is the interest is added continuously every instant throughout the year instead of just once a year or once a month like your typical interest. The formula that we're always going to use for continuously compounded interest is A equals PERT. And you could also see the formula with a function notation, the final amount with respect to time, or A of t. And so I'm going to keep it simple and just leave a capital A for our final amount. P is our principal, which means our starting amount, the amount that we invest. And then E is actually a number. It's not a variable. So we're never going to fill in E with another thing. E is approximately equal to 2.718. E is called the natural base, or the natural number. In this case, it's a base. And it's found a lot in math and science. It's actually found in nature. That's one of the reasons it's called the natural base. But it is a specific number, and 2.718 is just an approximation. It's actually irrational. It goes on forever, has no repeating pattern, and it's very similar to pi. We've kind of gotten used to pi means 3.14. That's an approximation to pi, and E always has this value. Then you have two things up in the base, up in the exponent that we've had before, which is rate. That's your interest rate, a percentage, usually written as a decimal, or always written as a decimal. And then time is your years. And both of them happen to be in the exponent this time, rather than having the rate down low and then the time up in the exponent. So this is the formula we'll use. Let's look at an example. Okay, let's say a relative puts money when you're born into an account and says that you need to leave it there. Your parents need to have you leave it there until you're 18 years old, and then you can pull the money out of the account. So let's say they put it in an account that's continuously compounded at an interest of 5%. And when you're 18 years old, they're going to let you take the money out of the account. They put $3,000 in when you were born. So let's see what happens. Our final amount will be the principal, which is always the starting amount. And then we're going to have the letter E, which is the number 2.718, but we want to use the letter E on our calculator rather than the approximation. The calculator has E above the division symbol, so if you ever want to use E, it's the kind of the shift to the division symbol. There's a little E up above there. So use that, and then take it to the power of 0.05 times 18. Now, if you have an older calculator, you'll probably have to put all that in parentheses so that it knows all of that as part of the exponent, not just the 0.05. If the calculator actually pushes the exponent up into a higher level, then probably you'll see that the 0.05 times 18 ends up all being up in the exponent, and as long as it looks like that, the calculator will understand it that way. So after 18 years of just letting your money sit in the bank, it has increased, more than doubled, and it is $7,378.81 approximately.